Hi, I'm James Alford,
I'm Justin Quattlebaum.
And I'm Slade Walters.
and this is our ELCT 201 end of semester project.
Our project is the analog on-off controller with wireless capabilities utilizing the Photon microcontroller. This circuit allows a user to set a set point using an app that controls the Photon over wireless internet. The circuit adjusts its output to the set point using various systems we will talk about shortly. A good way to think about it is a thermostat. You set a temperature and the system adjusts itself to a set temperature and then turns off whenever it reaches that temperature.
This circuit contains three subsystems. Subsystem 1 sets the window, which is called the dead zone, by the use of a trim pot, a photon, and 2 op-amps out of the LM324 package. The photon is powered by 5.2 volts in order to output 3.3 volts to the system. Subsystem 2 uses the last 2 op-amps out of the LM324 package and takes the upper and lower limits that were established by Subsystem 1 in addition to the feedback, which will be talked about in the next subsystem, to determine if the system will run in forward or reverse. If the feedback is lower than the lower limit, it will send out a forward signal. If the feedback is higher than the upper limit, it will send out a reverse signal.
Subsystem 3 consists of an H-bridge, a 12-volt DC motor, and a 10-turn potentiometer. The H-bridge is powered off of 12 volts DC, which we supplied from our DC power supply, and using a system of diodes and switches, it allows current to flow through either one direction or the other direction through the DC motor, depending on which signal it's receiving from subsystem 2, forward or reverse. The 12-volt DC motor, in turn, is connected to the 10-turn potentiometer via mechanical linkage, which serves as the feedback for subsystem 2.
The photon was the major point of focus for our circuit. The photon was powered by a DC regulated power supply. The oscilloscope shows the 5.2 volts input as channel 2 from the DC regulated power supply and 3.3 volts output from the photon as channel 1. We used 4 pins of the photon microcontroller, one for the 3.3 volt output, one to power the photon, one to ground the photon, and one for the set point. The Tinker app that goes with the photon allowed us to set the pins as digital read or digital write, or analog read, analog write. We used pin A3 as analog read, analog write. This allowed us to have a range from 0 to 4095, which translates to 0 to 3.3 volts.
This next picture is showing how we wired up the LM324 and H-bridge together before we connected the photon and the DC motor. And finally, here's a picture of the completed circuit with all the subsystems attached and the photon and the DC motor and 10-turn potentiometer, which served as the feedback, all connected together.
This is the Tinker function of the Particle app. This function allows us to change the analog write value of pin A3.
Here we're showing the dead zone that is created by subsystem 1 when we set a set point using the Tinker app on the phone.
Yeah, okay. Okay, I got you. I can do that. All right, sounds good, man.
This video shows our system functioning properly. It shows us using the Tinker app to set a set point and then watching the system adjust its output in order to move into the dead zone, which we set through a set point. This video shows another way to show the system functioning properly by physically changing the mechanical linkage and then watching it correct itself to the set point's value. Referring back to our thermostat example, this would be like the temperature in the room changing and the system automatically adjusting back to the dead zone without the set point being changed.